Okay, we're ready now to look at an example where we have a subspace, and we're going to have to prove this. So let's take a look at this. Is the set W, what is this set? It's the set of all ordered triples such that, right, the vertical bar means such that C, the last component C, must be what? A plus B. What is it? C must be the sum of the first two components. So could you list some vectors that are in W? Sure. Notice the 0 vector's in there because 0 plus 0 equals 0. Basically, you're going to add the first two components to get the last one. Here's some other vectors in the set. 1 plus 1 is 2. 7 plus negative 3 equals 4. 2 plus 3 equals 5, and so on. We can come up with many other examples. We only need to list a few, though. And then in the last example, we were able to quickly find a sort of a counterexample or an example that shows we were not closed under addition, or we can maybe find one that shows we're not closed under scalar multiplication. And in that case, we have a situation where the subset is not a subspace. But this time, look at this. If I add two vectors, let's not add the 0 vector to anything because we know what's going to happen there. But let's add these two vectors together. All right? What do we get there? 1 plus 7 is 8. 1 plus negative 3 is negative 2. 2 plus 4 is 6. So I get that vector 8, negative 2, 6. Is the vector 8, negative 2, 6 in this set? Well, what is 8 plus negative 2? It equals 6. Yeah, it's in there. The sum of the first two components will be in there. Well, try another combination. Let's try, this vector here and this one here. What do I get? 1 plus 2 is 3. 1 plus 3 is 4. 2 plus 5 is 7. I get 3, 4, 7. Is 3 plus 4 equal to 7? Yes. Okay, as we keep doing that, you're going to find that you can't find a contradiction. You can't find an example that shows you're not closed under addition. That doesn't mean you've proved that you are closed under addition. There is no way to go through that process because there are an infinite number of possible vectors here. Okay, and so we're going to have to actually prove that in general. Now, it may be it's not closed under scalar multiplication. Let's just try that. Let's suppose I multiply this vector by 2. What do I get? 2, 2, 4. Is the vector 2, 2, 4 in this set W? Yes. What if I multiply this one by negative 2? I get negative 14, positive 6, negative 8. Negative 14, positive 6, negative 8. Is negative 14 plus positive 6 equal to negative 8? Yes. And so on. So as I continue to try and reach a contradiction, try and find a counter example to show it's not closed under scalar multiplication, it just doesn't happen. And so what we have here is, or at least we're pretty confident that we have a subspace, but we have to prove it, right? We have to prove it. And we're going to use the theorem we talked about in the last video. We're going to prove it using the theorem basically that says if you have a subset of a vector space, then you need to just simply show it's closed under addition and closed under scalar multiplication. So here's the way we're going to do it. And I want you to pay close attention and to do your, this will basically be the proof in our third test. We'll be proving that you have a subspace. So I'm going to let two vectors be in the set W. Let's call U, and I'll let U be the vector U1, U2, U3, and the vector V, V1, V2, V3. So you want to choose two arbitrary vectors and let them let U and V be in, right, W. Let them be in that set W. Okay, it's important that you start in W. Just don't say there are any two vectors in 3 space. They have to be in W. That's important because we start with vectors in the set W, and we need to show these vectors when we add them or scalar multiply them, we always get a vector in W. And you do want to make it most arbitrary, right? So all these components have to have different symbols, letters, or whatever. I mean, you can use, A, B, C, and then D, E, F or something if you want to. These have to be different. Now, one thing we do know is when we say we're in W, we know some things about these components. For instance, here, if U is in W, then I know that U1 plus U2 equals U3, because that's what it is. To be in this set, the sum of the first two components have to be equal to the last one. And I also know that V1 plus V2 must equal V3. Okay, so that's the information I know. Now, from this, what we want to do is show we're closed under addition. So, are we closed under addition? Well, we're going to take these two vectors and add them together. Okay, and what do I get when I add these two vectors together? Well, we can do that. I get adding their first components together. Get the first component, add their second components, add their third components. Okay. So, is this vector now also in W? And this is the tricky part that I want you to be able to show. I want you to show support. I just don't want you to say yes or no or I don't know and not give any support one way or the other. And here's how you're going to do it. In order for this vector here to be in the set W, what has to be true? The last component must be equal to the sum of the other two. Okay. Well, let's see if we can get that. I'm going to start with the last component, U3 plus V3. Now, what can I say about U3 plus V3? Well, you can't just say it's equal to the sum of these two quite yet, but I can say U3, right, is equal to U1 plus U2, right? Because we know that. Do we know something about V3? What do we know about V3? V3 is V1 plus V2. Okay. Now, I would like you to show this one step because this is important. When we're talking about real numbers, right, which all these things are, U1, U2, V1, V2, we have the associative and commutative properties of addition. By using that, I can rearrange and regroup this to the following sum. I can do the U1 plus V1, right, U1 plus V1, group that together, and then the U2 plus V2. And this now is important because now what have I shown? U3 plus V3 is equal to U1 plus V1, which is the first component, plus U2 plus V2, which is the second component. So this information here tells me that this vector is indeed in the set W, and I know that W is closed under addition. So that's the first step in the proof. What's the second step? Show it's closed under scalar multiplication. So here you have to be careful. Don't choose any particular scalar. Let it be general. So let's let K be any scalar. And then I'm going to look at K times, and now I've got two vectors to choose. I only need to pick one. I'll choose U. You only need one to do this now. I needed two because of the addition part, but now I only need one. So what's KU? Well, I just multiply every component by K. So I get KU1, KU2, KU3. Now, is this vector always in the set W? Remember what the set W was? Set of all vectors, ordered triples rather, such that the last component is the sum of the first two. Well, again, I'm going to show this as an aside like I did here. I'm going to start with the last component, KU3. And what can I say about KU3? Remember what we know. What do we know? Real important what we know. Once we say that these two vectors were in W, we know these two things are true. So U3 is U1 plus U2, and I'm going to replace U3 with that. And then what? These are all scalars. I can use the distributive property, right? This is KU1 plus KU2. So it's a very simple thing, but you have to show it. You can't just state it. You just assume that I'm going to assume you know that. You need to show this very subtle and very trivial thing, really, if you think about it. But this is saying what now? KU3, the last component, is equal to what? KU1, first component, plus KU2, second component. So this tells me that this is in W, and therefore W is closed under scalar multiplication. So I've satisfied both conditions for the theorem, which is what we have to show we have a subspace. We have to show the subset is closed under addition and closed under scalar multiplication. So what is it we've concluded then? Is W a subspace of 3 space? Yes. And you should state that finally, right? So therefore W is a subspace of 3 space. So make sure you answer the question after you do all the work. Okay, let's look at a couple more examples, and we're going to look at some of the other types of vector spaces in these. The first one I'm going to look at is what we call a polynomial vector space. Trying to see if we have a subspace of a polynomial vector space. So let me explain this. We have W is what now? It's the set of all polynomials. Do you see this? The A, B, and C are the coefficients of a second degree or less polynomial, right? Such that what? The sum of those coefficients add to 0. Is this set W a subspace of P sub 2? What is P sub 2? P sub 2, this is the vector space, and it's of all degree 2 or less polynomial functions. Okay, so that P sub 2 is a vector space, and this indeed is a subset, because not all degree 2 or less polynomials will have their coefficients add up to 0. Okay, so again, what we're going to look at is what are some vectors, or in this case, what are our vectors? Our vectors are polynomials. What are some vectors or polynomials in the set W? All right. Well, first one I'll have you note is this. The 0 vector is in there. Now, what in the world is the 0 vector in this set? What are we talking about? Here's the 0 vector. It is 0 x squared plus 0x plus 0, which we probably could just write as 0 as in terms of the function. We normally, we wouldn't write this out as our function, but again, to emphasize the fact that the coefficients A, B, and C are all 0, right? And what is A plus B plus C equal to? 0. So the 0 vector is in there. What are some other vectors in there? Well, here's one. X squared minus 2x plus 1. Because look at the coefficients. What are they? 1, negative 2, and positive 1. What's 1 plus a negative 2 plus 1? That's equal to 0. What about this one? Was that in the set? Yeah. And now you say, wait a minute, there's no x squared term. Well, it's 0x squared plus 3x minus 3, but you have 0 plus 3 plus a negative 3, that adds to 0. A couple more. There's another polynomial that's in the set W. Add the coefficients. Notice there's no x term, but its coefficient is 0. Negative 7 plus 0 plus 7 is 0. And we'll do one more. I'll just make one up. What if we have 13x squared minus 10x? What's the constant term going to have to be for this vector to be in this set? Can you tell me? 13x squared minus 10x, what does it have to be? It has to be negative 3, right? So the coefficient's 13 plus negative 10 plus negative 3 equals 0. Okay, so, and we can go on many more. But, just list a few, and then we play the game again. We say, can I combine how? Adding or scalar multiplying some of these polynomials and get a contradiction. Well, let's try adding. Let's add this one and this one here. So what do I get? X squared no x squared term here, so x squared. What's negative 2x plus 3x? That's 1x, or x. So x squared plus x. 1 and negative 3 is negative 2. X squared plus x minus 2. X squared plus x minus 2. Is that polynomial in this set? X squared is 1 coefficient, plus x is 1, minus 2, 1 plus negative 2 is 0. So that's in that set. Okay? Well, what if I add, this one and this one together? What do we get? Negative 7x squared plus 3x. 7 and negative 3 is 4. Negative 7x squared plus 3x plus 4. Negative 7, 3, negative 7, 3, and positive 4. Do those add up to 0? Yes. Okay. As you continue to add these polynomials together, you're not going to reach a contradiction. You're not going to reach an example where it's not in the set. What about scalar multiplication? I think it's almost obvious. I think you can see that. If I multiply this by 3, 3x squared minus 6x plus 3. 3 minus 6, 3. Add those up, you get 0. And so on. So what's happening is, since I can't seem to reach an example that shows it's not closed under addition or scalar multiplication, then my hunch is that it must be a subspace. But again, I can't just state that. I'm going to have to prove that. And so let's look at how the proof would go. So I'm going to let P be a polynomial, and I'll just say ax squared plus bx plus c. And I need another one. I'll call that Q. And I'll let that be dx squared plus ex plus f. Again, I have to have different coefficients for these guys. And I want to make sure I say again that these, let these be in the set W, right? Real important. Okay. So what do we know if these are in there? What do we know? Very important. The only thing I know is that a plus b plus c must be what? 0, since this polynomial is in the set W. And what else do I know? Since this polynomial is in there, I know d plus e plus f is equal to 0. Those are the facts I know. Now, I use those facts to show closure under addition and scalar multiplication. So what is under addition? If I add these two arbitrary polynomials together, what do I get? Well, ax squared plus dx squared is a plus d x squared, right? I just add the coefficients. bx plus ex, b plus ex, and c plus f is the constant term. So is this polynomial in the original set W? Right, go back up here. What has to be true? The sum of the coefficients must be 0. So here's what we do to show this. We simply come down here and we write a plus d plus b plus e plus c plus f. Okay? So the sum of these things must be 0. Okay? You can't just state that they're equal to 0. You must show why, and it's just one subtle step again. What is the subtle step? Remember, A, B, C, D, E, F, all these are real numbers. So for addition, we have the commutative and associative property. I can regroup these any way I want. And the way I'm going to regroup them is how? Do you know how I'm going to regroup them? I'm going to group the A, the B, and the C together. Right? A, B, and C. And then add what? The D, E, and F. Why am I going to do that? Because look what we know. Look at the facts that we know up here. What's A plus C, B plus C? This thing here, I know is 0. This thing here, I know is 0. And 0 plus 0 is indeed 0. So what have I showed here? The sum of the coefficients of this polynomial is equal to 0. So this is the important step you have to show. This tells me what? That this thing is in W, and we're closed under addition. And then again, closure under scalar multiplication. So we're going to let K be any scalar. Right? And then we're going to look at k times either one of our two polynomials. We can choose either one, doesn't matter. I'll choose p again. And if I multiply this by k, I distribute over and I get ka x squared plus kbx plus kc. Now, is this polynomial in the set W? Well, again, we're going to have to check, and that is if the sum of its coefficients, which are ka plus kb plus kc, if this is 0. Okay? Think about the facts that we know up here. How can I use these facts to know that this is 0? I think you know already, but you have to show it. You just can't say it's 0. What are you going to have to do to get there? You're going to have to do what? Factor out a k. Right? What does that leave me? A plus b plus c. Right? And what is k? A plus b plus c. That's k times 0, which of course is 0. So this tells me again that the sum of the coefficients for my polynomial equals what? 0. And that tells me this is in W, and we're closed under scalar multiplication. So therefore, W is a subspace of P sub 2. And don't forget to answer the question. Okay, we're going to look at two more examples in this video. Again, we're going to look at the set of all degree 2 or less polynomials as our vector space. And we're going to look at a subset, the set W of all degree 2 polynomials. Was that just the same thing? Set of all degree 2 polynomials? No, remember this is the set of all degree 2 or less. So what's the difference? When we think of degree 2 or less, we've got ax squared plus bx plus c. But here, degree 2, the a cannot be 0. And so what are some vectors in W? Well, x squared is, 3x squared is, 7x squared minus 2x plus 4, or 5x squared minus 1. And we can go on and on. As long as there's an x squared term there, then we're going to have a polynomial in the set W. Okay. Well, I think already some of you are saying, something seems fishy here, and you would be correct. But this set is not going to be a subspace. But we're going to show it again by a specific counterexample. And here's what I'm going to do. I mean, there's lots of ways this can be done, but let me just think of x squared, simplest one here. That's a polynomial in the set W, but if I simply multiply by 0, right, what do I get? I get 0, right? I get 0x squared plus 0x plus 0. 0 is not a degree 2 polynomial. This is a degree 0 polynomial. And therefore it's not in the set W. In fact, this is the 0 vector for polynomials. 0x squared plus 0x plus 0. And that's not in the set. And so we know already it's not going to be a vector space. But again, I can show closure. That's not closed, rather, right? Not closed under scalar multiplication. It's also not closed under addition because x squared is in the set W, but so is negative x squared, right? X squared and negative x squared are both in W, but if you add x squared and negative x squared, you get 0 again, and we would have a situation where we're not closed under addition. You do not have to show both that it's not closed under scalar multiplication and it's not closed under addition. You only need to show one, when you're showing it's not a subspace. Okay, one more, and then we'll end this portion, this video, and the next video we'll continue with some more examples. Is the set of all 2 by 2 invertible matrices a subspace of M22? Now M22, right? This is the set of all 2 by 2 matrices. That's a vector space, but not all 2 by 2 matrices are invertible. Okay. And I think, again, some of you are already noticing something and already know what the answer to this is. But let's take a look at this. What are some matrices in this set? Let's call this the set of all 2 by 2 invertible matrices. Let's call that W. So some matrices in W. What are some matrices? Well, it's got to be invertible. You remember how a 2 by 2 matrix is invertible? Do you remember? If their determinant is not 0. So I mean, what's some examples? 1, 0, 0, 1. The identity matrix, which determinant is 1. That's invertible. Right? Here's another matrix. I'll just make one up. 3. Let's say 3 times 2 is 6. 1 times 5 is 5. 6 minus 5 is 1. The determinant is not 0. Anyway, I can create many examples here. Here's another one. Just a diagonal matrix, right? 80 minus 0 is 80. I mean, I can go forever finding 2 by 2 matrices that are not invertible. But I think you know one important one is missing from this list. But here I'm just going to say that, again, if I were to take this matrix here, right, which is in W, and if I multiply it by what? By 0, right? If I scalar multiply it by 0, then I get the 0 matrix. Is the 0 matrix invertible? No, it's not invertible. Its determinant is 0. And so this is not in the set W. We're not closed under scalar multiplication again, and so W is not a subspace of M22. Okay, so these are a little different, especially proving that you have, I think most of you are pretty good about showing we don't have a subspace, coming up with a specific counterexample. There we don't need to prove it, but it's when we're proving that we do have a subspace you're going to have to work on. And so give that homework in section 4.2 a try. We're going to come back with another video and continue talking about some other topics in section 4.2.